Okay, so let's share my screen. Okay, so yesterday we discussed about the different biasing. Not about exactly biasing. We had tried to calculate the different voltages and currents across the different points of transistor. Okay, so that part is called biasing. Although I not explicitly told you that we are trying biasing, but all those calculations we have made is the different operating points of the transistor. Okay, so what we have done, we have given a base voltage we call VBB here. Okay, again we have put some resistor on the collector part. Again, some voltages, bias voltage or that part, and I can some kind of. So what is I'm giving here? I'm giving different voltages and different currents and different ports of the transistor. Okay, so there are base junction, the collector, then emitter. So what I'm trying to do, I'm trying to give different voltages and current at different terminals of the transistor. So that is called biasing. What is called biasing? Okay, in other words, if we need to have a simple definition of biasing, biasing is nothing but fixing the operating point of the transistor so that the transistor is ready for its application. It can be as a used as amplifier, it can be as a switch, it can be as a filter, or there are n number of applications. So biasing is making sure that the transistor DC currents and voltages are constant and appropriate. Okay, so we already know there is an active forward active region where uh, base emitter junction has to be forward biased and collector base junction has to be reverse biased. Okay, then we'll get some special properties. Okay, we already know the special properties which help transistor to work in some specific application like amplifier, and some other points for working as a switch. Okay, so here we'll discuss the active region. What is active region? An active region we already discussed. Okay, this is I'm drawing the structure of the transistor. Okay, and I'm telling this is N, this is P, this is N. Okay, so you can see here the base junction or base region is very small. Okay, so this we have already discussed. The base junction or base region will be very small compared to collector and emitter. Okay, and one more thing, first thing is base width will be very small, base width will be small. And what are the other thing we discussed? And the specialty is emitter junction will be highly doped. So this is emitter, then this N plus. That means heavy doping of N carriers or electrons. Okay, on the emitter side. Okay, so which is emitter here? So I call this is emitter, and this is base, mid push, and this is collector. And another thing you can note is here the collector size is a bit higher than emitter size. Okay, you can see the width also. If you see the width also, you can see emitter width is a bit less than collector width. We'll see why. We'll see later. Okay. So what are the things here? Emitter should be higher doped than collector. So we call N plus, and width will be small, and collector will be having larger length. Okay, because it's going to collect electrons. So let us give it small, more length. Okay, so what else? Now the conditions to make the transistor work in forward active region or active forward region, whatever. In active region, my base emitter junction should be forward biased. So here we have PN junction. So how to make it forward biased? Yes, this should be forward bias. This should be given a negative, and it's negative, and P is plus. So this is a forward bias. Okay. And what are the other things? Our base collector junction should be reverse biased. Okay, very important. You have to remember these things. It's very important. This is forward bias base emitter junction, and the other junction should be reverse bias. So let me draw reverse bias here. So reverse bias means N should be plus, N should be plus, and B should be minus. Okay, you remember this thing? Okay. So we can, from here we can see the base collector. You can see what is the base. Base is, this is point is base. Base collector. Now base is at a lower potential than collector. Is it visible? Yeah, because this is plus, collector is plus, base is minus. Because there's a voltage source, we can see that collector is at a higher potential than base. Okay, so this is just an observation. I think you can draw this in your notebook and just understand that the base. Uh, I'm audible, right? Everything is fine, right? Okay. I hope everything is working fine. Just to make sure that I'm audible.
Yes, sir, audible.
Okay, thank you. Fine. Okay. So you just need to draw this in your notebook so that you understand what we are trying to do. To There are different combination permutation of biasing a transistor. They can have reverse bias in base emitter junction and forward bias in collector base junction and reverse biasing both sides, forward biasing both sides. Okay, and we have emitter collector junction also we can make, not junction, sorry, intercollector junction also we can connect using a battery also. But there are different possibility of biasing. In this biasing we have selected two biasing, that is forward bias in the base emitter junction and reverse bias in the collector base junction. Okay, so someone can ask why I have selected this thing. Simple, by experimentation or by trial and error I have found that this configuration is best. Why? Now we will see why. Okay. Now, so this is one configuration. So yesterday I drawn another configuration. By practice, we don't give the biasing like this. What we'll give? We usually we usually give in a different style. So what is the style? We usually don't give this thing here. So for that, we give say voltage on the collector to emitter. Okay. So what we'll give? We'll do like this. Okay. So we give a voltage here like this plus, okay, and we call this voltage yesterday in a lot of examples you've seen, this is called this VCC. And what is this voltage called? VBB. VBB doesn't given on base side, so it's BBB, and collectors are VCC. Now by default still you can still calculate the voltage on collector to base, VCB. VCB. You can see that VCB, this will be plus and this will be minus. So we can see still the collector voltage will be at higher potential than base voltage. That is why it is still keeping the reverse bias of the collector base junction, right? That you have to understand. What you are trying, we are keeping this node voltage bit higher so that the collector base junction is still a reverse bias. I think this is simple. Instead of that in connecting two batteries like this, I'm putting one battery so that I have a common ground. You getting? Now, in this connection, what I'm advantages, I have a common ground of both batteries or both cells having common ground instead of the previous connection. But still, you can see the base emitter is still forward biased and base collector is still reverse biased, provided this point VC C or point C or collector is at a higher potential than base. Then I can see the base collector or collector base junction is also reverse biased. Okay, so this connection is what we use usually apply because it's positive characteristics. Now you can ask what are the positive characteristics. Okay, now yesterday we discussed about the beta and all this current gain, DC current gain. Now we assume that yes, transistor we are getting a beta. That means IB or IC equal to beta times IB. Okay, so now we will be thinking or we'll be explaining why we are getting a higher beta times something. So before going to that, I think we can have one more example of yesterday's a new kind of circuit. Exactly same. Yesterday we had discussed two types of circuits. I will give you one more circuit which is also very used in practice. So after calculating the biasing point of this transistor also, we will explain how we are getting a beta times gain or beta times gain in the collector current over a base current. Okay, so this thing I think we have not discussed yesterday. So this is circuit, this example. It's a very commonly used circuit. So this is very important. So we'll draw this. This is a transistor NPN. I'm using NPN transistor. Now, what I'm doing, I'm just trying giving a resistance over stop. Okay, and I'm also keeping a resistance over the bottom. Yesterday we have seen one example like this: emitter resistance and collector resistance. Okay, now I am keeping again a voltage divider by, I think you remember this thing. What is this? Two resistance connected in series with a voltage source VCC. Voltage source here also VCC. You remember this? We already discussed in multiple times, but in the networks analysis and also in the basics of the circuit, electronic circuits, we discussed the voltage divider bias. What is voltage divider? Voltage divider is if I divide the voltage source VCC here into two voltages using two resistance. So voltage drop across these two resistances will be directly proportional to the magnitude of this resistance. Okay. So correspondingly, now what I'll do, I have two voltage drops. Okay. For example, I call this resistance RA or R1, this R2. Okay. So what I'll get, I will get a voltage drop V1 voltage drop across R1 and another voltage V2 which is dropped across R2. Clear? Very simple. Two resistances and there will be current passing through this. There will be current, for example, there's a current I. There's a current I passing through it. So what is the voltage across R1? I into R1. That's equal to V1. Now what is the V2? I into R2. That is equal to V2. Okay. So we can just see that the voltage drop across this resistance is directly proportional to the magnitude of resistances. Okay, so we have uh, two voltages across these two resistors. That is the only thing. Okay, we are designed in such a way that we'll get some two voltages over this resistor. Now what I'll do, now I'm just connecting the midpoint of this junction of the resistance into the base of the transistor. Getting? Okay. Now I'll just name the resistances. You know, this is the collector resistance RC and emitter resistance also we have RE, and this R1 and R2, let it be the same. R1 is the top resistance, R2 is bottom resistance. Okay, you should remember there's a voltage drop across R2. Now this voltage drop is going as the input to the base of the transistor. So again, I'll draw the terminals. This is base junction, this is collector junction, this is emitter junction. Okay, so right now using these two resistances, what I'm trying to give voltage V1, which is drop across R2 to the base of the transistor. Okay, but should remember that I have two another resistors RE and RC also. Now we can see another interesting thing here. You can see these two resistance voltage sources VC. These two VC and VC both are having a positive voltage. For example, plus 5 volt, plus 10 or whatever. So these are both are same here. The magnitude wise both are same. Okay, so what I can do? I can combine this together. Okay, so what I'll do? Both are VC, so why should I use uh, two different voltage sources? For all practical purposes, I'll just show it as single. Okay, so I connect into a single point because both are same. Okay, so the VCC have plus minus, say positive voltage plus VCC, and the reference is ground. Okay, now I simplify the circuit. I have a common voltage source, and this is equivalent to connecting a voltage source like this. This is equivalent to connecting a voltage source. Now, okay, this is like plus minus. I'm getting a VCC equivalent to, and this is ground. This is equivalent to giving a voltage across the base also. This is V1. This is V1. Okay, so the red is equivalent voltage what I'm giving. So you can see here also what I'm trying. I'm trying to give the base emitter junction a forward bias and base collector junction is reverse bias. Clear? Although I'm using same voltage source, but the concept is same. I need to operate the base emitter as in forward region, or and the base collector base in the reverse region. Okay, using only one voltage I'm using. So you have to design the resistance accordingly. We also seen one example where we have wrongly taken one resistor and the transistor was not acting properly. Okay, so I think this is clear. Now I'll go back to our earlier circuit, nature circuit. Yeah, this is our circuit. Now your VCC, we have R1, R2 in the base circuit, which is giving a V1, just drop across R2 to the base of the transistor. And okay, now this is another type of circuit. This circuit is also called one kind of biasing called voltage divider biasing. Okay, why it's called like though? Because we have two resistors R1, R2 creating a voltage divider. Okay, and that voltage divider creates a voltage V2 or V1. Sorry, here I'm told as V1, so leave it. You can remember the V2 or what voltage V2. It doesn't matter, but whatever voltage across R2 is given to the base of the transistor. Okay, so this is called voltage divider bias. Voltage divider biasing. Okay, that yesterday we have discussed a lot of other time biasing also. It everything has its own name, but we just to understand what our main aim is to fix the DC currents and DC voltages across different points of the transistor, so that the transistor working in proper region or active region, old region. Okay, so I'll give you some values so that we get oh okay, I'll give you some values so that we'll get a feel, so that the circuit we are trying. So again, I'll draw there's a transistor and resistance RC top, RE at the bottom, and I counted together, and I have two resistances here, R1, R2 as a voltage divider grounded, and the middle point of the resistance connected here, and these two resistances are shorted, and this point I call plus VCC. Okay, now I'll give you different values. Okay, so value of the VCC I can take it as plus 10 volt. VCC is plus 10 volt. Okay, now RC you can take, this is RC, this is RC equal to 3.6 kilo ohm, 3.6 kilo ohm. Okay, and RE, you can draw this circuit in your notebook. RE equal to 1 kilo ohm. Okay, and R1 you can take it as 10 kilo ohm, and R2 you take it as 2.2 kilo ohm. Okay, 2.2 kilo ohm, R1, R2, RC and RE, we have done everything, and we have VCC of 10 volt. Okay, VCC is going as 10 volt. CC should not VCC right like that. Okay, VCC is 10 volt. Now the question is, yeah, this is a silicon transistor, and yes, find the different voltages and current at different points of the transistor. You can also find the power dissipation of the transistor. This is maybe the question. Now, how to start with and how to find all the currents, voltages, and everything. Now, you may ask, what is the beta? Okay, if sometimes if we are not giving the question the beta, you can assume a beta. For example, here if there is nothing is given, you can assume that beta. You not tells us we don't know beta. Usually, these kinds of beta will be depend upon the transistor. So usually in some questions we can see the transistor number will be given. For example, in some questions you may given the transistor nearby transistor will written like 2 and something 3904 something. Okay, so what is the idea? This means that this transistor name is 2N3904. So if in any circuit you find that if you download some circuits from the internet, you'll find uh, this thing very commonly. There'll be name of the transistor, and find how to find the beta. All those things you just need to go to the internet and search for the data sheet of this transistor. Okay. Okay, so that is the, then if you search the data sheet of the transistor, you can find the beta of this transistor. Okay, so this is the way. So here I'm giving you the beta. I'm giving the beta of the transistors and take it as 250. Okay, so beta is also given 250. Okay, I want you to take 5 minutes and think where I'm going to start and how am I going to find all those currents and voltages like VB, VCB, VCE, and all the voltage drops across R1, R2, RC, RE, and all those things, and total power dissipation of the transistor. Take 1 minute, at least find the way. I'm not telling you to calculate everything. At least find some way to find all this, how to start with and how to continue. That's it. You take your own time, just think on your own. How am I going to find all this currents and voltages? I think today very less students have joined. Okay, so how to start with? Can you tell me? Is 1 minute? Okay, so you have tried it. So how to start with? Yeah, anyone? Any comments? I don't see any comments, I think. No comments. So how to find IB from here? First, IB relationship with IC, everyone is aware of. So say IC equal to beta times IB. Okay, so how to find beta is given 250. So we need to find IB so that we can get IC. If IC is found, we can easily find the all other voltages. This IC is this current passing through this collector to emitter. So if IC is found, we can find the voltage drop across RC resistance, voltage drop across RE resistance, and everything. Okay, then we can find the power dissipation as well. So anyone? So anyone has any suggestions? Yes? No? Nothing? I think there is no suggestions or no questions. That means two things. Either of the two things. Either you are understanding everything, not losing anything, and else you're not understanding anything. Okay, so no comments. I think this is so easy for you. I think
1 minute, sir.
yes, yes. I'm not telling you to calculate everything. I'm just asking you what is the way to proceed, how to start calculating something so that we can find the other things.
Two loops we can see.
What?
So two loops we can see first upper side and second lower side.
Acha, you're telling this thing,
Yes,
one, this thing, two. Yeah, this is also fine. Then,
sir. We can apply KVL law in first loop.
okay, we can apply KVL law. So, but here, uh, what is VC? Here, there's a collector terminal in the top, base terminal here. Okay, so you don't know the current passing through this thing. This is called I. You can say I or
Yeah,
whatever.
yes,
And
sir.
you don't know current passing through here also. And
Yes,
you
sir.
also don't know what is VCB also or VBC. There are three unknowns, and it's very difficult to find anything because I is passing through this time, another current IC is passing through RC, and VBC. So I think that will not be a good option. Is there anything else, others of any other option? Apply KVL in second loop. Yeah, second loop. Yeah, another person's link. You can apply KVL in second loop. Yeah, that is one option. But still, here also we can see. If you start with that, there's a current passing through this I call I, and there's another current called IE, emitter current IE that we know, and we know one voltage, base emitter voltage that we know, right? Yeah, we know. Here also there are two unknowns. Which are the two unknowns? One is IE, I don't know. This current I don't know at least right now, and this I know. Yeah, definitely this I know. Yeah, the second loop is more important. You're right. Second loop is more important because we have less number of unknowns there. We know the V base emitter voltage. Okay, so this is the idea only. Yeah, first, first what I'll do, first I'll try to calculate the VR2. That is what is the voltage happening in my base. That means if I calculate this voltage V2, if I calculate this voltage, then I can calculate voltage at this point VE, right? Voltage at this point VE is how it is V equal to I into IE into RE, right? But we know RE, but we don't know IE. But we know one more thing, the base emitter voltage that we already discussed. This is base, this is emitter. What is that voltage? VBE of a transistor, of a silicon transistor, that is 0.7, we know. Okay, so another very simple thing is the V2. If you take the Kirchhoff law, we can see from this point to this clockwise direction, we can see V2 voltage will be drop across VBE and RE. Right? This simple Kirchhoff law. So using that Kirchhoff law, I'm writing this equation V2 equal to VBE VBE plus VE voltage at the emitter VRE. You can say VRE or VE, whatever. VRE. Okay, voltage across resistance E RE. Getting? Now here we can have two things now. What are the two things? V2 I can calculate easily. V2 I can easily calculate the voltage divider. VB I already know. 0.7. Now I can calculate VE, right? Using this tool I can VE. I know VE is nothing but IRE. So I know RE already. So I can find IE from there. Okay. So when you know IE, then you know beta. You already know beta. So we know we can calculate IC. You know IC and IE as a relationship, that is alpha. That is IE is equal to alpha times, sorry, IC equal to alpha times IE. That means IE is equal to IC by alpha. So IE divided by um, beta divided by beta plus 1, that's nothing but substituting beta for alpha, we'll get IC. Okay, when you get IC, this is the current passing. So RC also. So we can find the voltage of echo VRC, we can find, right? That is nothing but IC into RC. Okay. So when you got that voltage also, we got VRC and VRE. Voltage drop across RC and RE. So the rest of the voltage drop of the input 10 volt will be dropped across VCE. VCE. Okay, we got VCE also. Okay. So we got that IB we know already. IE minus IC equal to IB, or I equal to IB plus IC, whatever. Okay. So this is the way. So let's start once again. Again, I'll draw the circuit of the voltage divider bias. Start with the transistor, and I have emitter resistance and the collector resistance. Collector resistance is almost in every biasing or every transistor circuit. VCC. And interesting point is I'm using a voltage, two resistances in series to get my base voltage, and this is called voltage divider biasing. Okay, so the two resistances R1 and R2 used for dividing the voltage source VCC, and we already know RC and RE we already know. Okay, so what is my idea? First I calculate V2, which is the voltage on the base and ground, which is input to the VBE and the resistance RE. So how to find V2? V2 equal to VCC into what the word bottom resistance R2. R2 divided by sum of resistances R1 plus R2. So what we are getting 10. VCC is 10. And what was the value of R2? I think it's 2.2 kilo ohm. 2.2 kilo ohm divided by R1 was 10. So 10 plus 2.2. And kilo numerator and denominator get cancels. So what voltage I'll get? So V2 I'll get 1.8 volt. Now someone may have some question here. How can I exactly calculate the value of V2 here at this point? You know, because obviously this doubt you should have, because there is another path. Not only there's one resistance R2 here, there is another path also going to the base of the transistor, right? So there are two paths actually, right? There are two paths here. So I cannot take this resistance as R2. This is R2 and a parallel combination of another path, which is having a base emitter junction of transistor and a emitter resistance, right? So I cannot exactly tell that the voltage V2 is exactly this one, 1.8. Okay, but still, this I'm using an approximation. I'm not telling this exact. For practical purposes, we can assume that whatever V2 I'm getting is drop across VBE and RE. Okay, so if you exactly go for accurate analysis, still there may be some variation, maybe 0.01 volt or 0.02 volt. Okay, so that is why we are having a standard biasing techniques. Standard biasing techniques where the resistance magnitudes always do matters. Okay, so if you can see the R2 value is 2.2 kilo ohm, which is less than R1, which was 10 kilo ohm. Okay, so like so right now I think you understood the Thevenin theorem. Here we may apply in the advanced circuit, we may apply Thevenin's theorem. Like what is Thevenin's theorem? In a complicated circuit, we simplify the complicated circuit by considering an equivalent voltage source and with a series resistance. For example, VTH. I'm assuming VTH across this base of the transistor. Okay, so the VTH is an approximation, not approximation, VTH is a net voltage which is applied across the base of the transistor. Okay, after simplifying the voltage divider, R1 and R2 is a voltage divider, then simplifying all those things, and I'm finding net voltage across the base of transistor. So this is what I'm right now done is a approximation, although it's not perfect, but for all practical purposes, I can assume this V2 as VThevenin. Now, if you ask me why it is equal to VThevenin, why can I say VThevenin is perfectly equal to V2? I'm not saying it's perfectly equal to V2, but for my calculations, that error is okay for all practical purposes. I can live with that error. Okay, so maybe in two class we'll discuss how this assumption is possible. Okay, for that we need to understand a bit more about the transistor internal working, internal resistance of the base emitter junction, okay, etc., and the current and why. So that we'll discuss some part today. The rest we'll discuss next class. Okay, so what I have done here, there's a voltage divider R1 and R2, and I have calculated net voltage across R2, that is V2. I consider V2, which is dropped across VBE and RE. And I consider the theory it is equivalent Thevenin voltage. It is given to the base of charge. With the Thevenin voltage always have a resistance also in series. I may just refresh your knowledge. This is R Thevenin. R Thevenin voltage is going to the base of the transistor. Okay, so that was a bit about theoretical thing, but practically I can live with the V2. V2 is very fine for my all practical purposes. So how to calculate V2? VCC into R2 divided by R1 plus R2. So I'll get 1.8 volt. Okay, so I got 1.8 volt over this point at 1.8 volt. Now this 1.8 volt at this node. Now this is drop across VBE and RE resistance. So right now what I can write? Now I can write one more thing. So I already got V2 is equal to 1.8. So now I put the value of V2 in the other equations. What is my other equation? This is equal to V2 equal to VBE, Kirchhoff law, VBE plus voltage drop across RE resistance, VRE, I can call VRE. Okay. So I know V2, what is V2? 1.8. And VBE, I know 0.7 plus VRE, voltage drop across resistance RE. Notation may be slightly changed in different textbook, but you should know the fundamental conceptually this voltage drop across RE resistance. So I can say VE or VRE is nothing but 1.8 minus 0.7, that is 1.1 volt. Okay. Now what we got? We got VE. We got VE. This voltage drop across RE. This is nothing but 1.1 volt. Now, once you know the voltage drop across the resistance, and the current voltage drop across resistance and the magnitude of resistance, you can easily find the current flowing. Okay, so what is VRE? VRE is nothing but I emitter into RE. You already know RE, so I equal to VRE, V drop across emitter divided by R emitter. So now VRE we already found 1.1. Now R emitter we already know this is given 1 kilo ohm. Okay, so we can get 1.1 milliampere is my emitter current. 1.1 milliampere. Okay, now we got IE also. Now when we got IE, now how to find the other thing? We know IE equal to something. Now we have to find IC. So IC and IC. So we have IC divided by alpha. That is That is, so I can write IC equal to IE into alpha, right? That is equal to IE into what is alpha? Beta divided by beta plus 1. Okay. So we get 1.1 milliampere into 250 divided by 250 plus 1. This is this is IC. So you can see one more thing, as beta is increasing. Beta value is 250. 250 numerator, 250 denominator. Here also I can have a very good approximation for practical purposes like 250, 250 cut. What I've done, I just approximated this and cutting, and this I neglect this one. 250 by 251, it is around 0.99 something. So here also what I have done, IC approximately equal to IE. I can take a very good approximation for all practical purposes. Okay. Although there will be slight variation, but I'm telling you, this is quite easily, even in exam questions also you can write IC approximately equal to IE. Because this is usual practice. Because beta is very high, 250, 300 or some value. So it doesn't make much difference or much error in this calculation. And this helps us to increase the speed of calculations also. Okay, so for all practical purpose, I say we can take IC approximately equal to IE. Okay, okay, so I got IC also. IC is around, you can say 1.1 milliampere only, same as IC. Okay, now if you know IC, we know voltage drop across resistance R. VR or which RC, collector resistance, RC. That is IC into RC. Okay, so IC we know 1.1 milli into RC. What was the value of RC? It was 3.6 kilo ohm. Okay, so I can see these two cancels, kilo and milli cancels. So then I have 1.1 into 1.1 into 3.6. That is voltage drop across resistance C will be something. How much it is? 1.1 into, yeah, 3.6. This is 3 point here. 3.6. I think it will be 3.96 or something like that.
3.96.
Yeah, 3.96 volt. Okay. So what is this? This is a voltage drop across RC resistance. RC resistance. Okay. So what we got? 3.96 drop across. So what do we not got? The resistance RC, the transistor base, sorry, collector emitter, then resistance. So this is VCC. This is 10 volt. So right now we got voltage drop across the resistance RC. That is, this voltage drop is 3.96. Okay. And this voltage drop we already found. I forgot how much was voltage here. 1.1, right? 1.1. That is, here 1.8 was here in V2. And then what 1.8 was drop across here, 0.7 minus 0.7 here again. Then again get 1.1 here. Clear? So that 1.1 was dropped here, 3.9 was dropped here. So how much is dropped here? You can see 10 volt was the input source. According to Kirchhoff law, whatever input you are giving to a circuit, it has to drop across the closed path. Okay, so 10 volt is the input source. So 3.6 is dropped here, 1.1 is dropped here. So here is voltage drop here. Here is VCE is 10 minus. This is C. This is C. So what I'm calculating is VCE. VCE equal to 10 minus 3.96 minus 1.1. So how much you'll get? That is 10 minus 6 point something. No, 5
So
point
4.9.
4.94. Answer? You're telling answer? Yeah,
Yes,
answer
sir,
is
it's
4. Yeah, so I'm just 4.94 is the VC directly link. So this much voltage is across collector and emitter. Okay. Now we already discussed this voltage and this current is very important. The current flowing through this circuit is IC and I, and this voltage 4.95 very important, because this is the most important thing in a transistor, the collector characteristics, collector current and collector voltage. Even one amplifier in the output, the transistor will be connected to some other circuit, loudspeaker, or whatever. So this point, the collector current and this voltage decide the operating of the transistor. So this is very important. IC and this. Okay, so we calculated VCE 4.94, and I think nothing more is need to be calculated. That is sufficient. Now we can, if you require, we can calculate an IB also. IB, you can say, already IC. So we can calculate IC and beta. You already know, so you can calculate IB. So here we had done approximation. What is IC approximately equal to IE for fast, for speed up our calculations, and doesn't make much error. Okay. So ideally, you can say if you that approximation, you get IC equal to I, then IB equal to 0. So don't need to worry. IB you'll get it. If you want to calculate IB, you can calculate it without any problem. Okay. But most important thing is VCE and IC is the most important parameters of a transistor. Now, what is the power dissipation? If I tell you calculate the power dissipation, P is equal to IC into VC, operating voltage, the transistor into operating current IC. Now IC is I don't know 1.1 milliampere into VC is 4.94. 4.94 is 5 into 1.1. So around you can see this approximately around 5 milliwatt, approximately greater than 5 milliwatt. Okay, this is greater than 5 milliwatt. Okay, so when you want to buy some transistor of this wattage, you have to go and buy a transistor of around maybe 100 milliwatt working. We usually get in watt, maybe half watt, 1 by 4 watt. But you can get a transistor of 50 milliwatt. So we'll take the upper limit. You can buy a higher tolerance for a tolerance. Okay. I think so. This is called voltage divided by. Now I want to discuss final thing beta regarding beta. So we already do again the transistor which we have used till now. This is N, this is P, and this is N, this is P, and this is N. You can see the base is smaller width and length, and this doping is much greater in emitter, and length of the collector is much greater than the emitter. So these are the things. Now I'll give it a forward bias. For the forward bias, this should be forward bias plus in the P and minus at the end. Again, I'll give a reverse bias here, plus in the N, minus in the P. Net effect is same. Okay. Now, there are 2 points we discussed. One is the base junction length is very less. Now we'll start understanding what is the gain, how is the gain coming. Now, for example, now all the electrons of the N plus region will be repelled from the voltage source, and there's a plus in the base. Getting? And we have another plus in the collector also. I'll draw the collector part also. So this is collector, this is base, this is emitter. Okay. So all these electrons. So the doping of the emitter is very high. Lot of electrons or current carriers, that is electrons, are in N region. In P region will be a lot of holes, but length of P region is very small. Okay, so I can say the number of electrons going from N to P is very high. This is I'm denoting by arrow. Lot of electrons are going from N to P region. But same time, some holes of the P region will be trying to come to N region. So there will be very less, but still there will be some holes coming to N region because of the electric field. Okay, but still the magnitude of electrons going to P region or the depletion region junction is much greater than the holes of the P region. Now, all the electrons which were reached the junction, that is here, junction here, are two options. One is either they can go straight to the collector, and the option they can go to the voltage source, is plus, which is already plus. So there is a dilemma here. In this junction, what will the electrons do? Whether they will go to the left or they will go straight to collector. Yes. Now, this is very important question. This is what makes the transistor work as we desire. a very good gain of collector current, very good ratio between collector current and base current. So what ideally we want, we need all the electrons to go to collector rather than base, right? Such the in such a way that we reduce the base current to very minimum. At the same time, the collector current is very significant. So what we'll do, that is why we reduce the base width to very minimum. The base width of a transistor, base emitter junction, or the base region of the transistor is made so small so that we have very less electrons going from entering from the emitter, going to the base to the battery source. Plus minus battery source plus minus. So I don't want many electrons going to that region. I want very less electrons. So definitely there will be some electrons going which were already in the base region coming from the emitter going to the battery source. But majority of the electrons will be going to the collector region. Now another reason of majority of electrons going to the collector region is we already seen last time that the collector base junction is also collector is also having a higher potential than base. You remember? We have discussed this thing. If you see in practical circuit VCB, this voltage will be higher than base region. Remember? Because the collector base junction has to be reverse biased. So this is more plus than this. So the collector terminal has more plus than the base terminal. This is another reason why majority of electrons go to the collector than the base. So majority of electrons from the base region who are coming from the emitter region will go to the collector rather than to the base voltage source. Okay, so I can say IC is much greater. IC is much greater than IB, at least here. Why? There are two reasons. One is base region is very thin. Okay, so all electrons cannot jump to the base. We can directly jump from here to here. No, there is no time left also because electron doesn't have much time because okay, because the base is very thin, and one another reason is there's always a electric field. You know, collector. There's always electric field which is attracting the electrons toward the collector. So majority of electrons go to the collector rather than the base. They don't have a time to divert the steering, change the gear, and go to the left towards the base. Okay, one is electric field. There's a more electric field on the collector side, more attraction. Another is base is so thin. Okay, and we'll pump more and more. We dope the emitter very highly. We dope the emitter very highly. That is N plus. We already have very high doping in the emitter terminal, so that we have major generation. More of the electrons are generated from the emitter, and it emits towards the base and jump to the collector. At the same time, where IB is very less than IC. Okay, so because of the electric field, because of the very narrow base width, and because of the high emitter carrier density, so we have IB is much less than IC. Okay, so this is the reason we get a DC current gain. What is DC current gain? This is from beta. This is the ratio of IC to IB. So IB is very less and IC is very high. Okay, so this concept you have to understand. This is one of the important concepts. Sometimes someone may ask you in the interview or whatever. So why this? Why? There's a lot of why question in transistor. Why IB is much less than IC, etc. etc. Why active biasing? Why in the forward region? Why not others? Okay. So although in this course we don't go deep into this, if you want to explain fully clear, there is another course called Electronic Devices Physics, Physics of Semiconductor Devices, Fundamentals of Semiconductor Devices, Physics of Semiconductor. This is another field where we can explain this mathematically. We won't go to deep in that field because we are more interested in applications like amplifiers, filters, op-amp, and all those things. So this is another itself another course. Maybe you can take some. If you're more interested, you can take this higher studies. If you're going for VLSI microelectronics in your higher studies, you definitely take this subject, device physics or VLSI semiconductor physics, whatever. It is somewhat related to nanotechnology because it is like quantum physics are coming to picture. because as transistors is becoming smaller and smaller, there are quantum effects. There are it is more of a mathematical and practical because we can design, we can fabricate, you can put more new chemicals, new structure of transistor can be implemented, and a lot of work going on in this field. Of course, semiconductor device physics. Okay, but we are not going to deep all those things. We are just interested that why IV is small, why IC is large, and how the DC gain is coming, and that is sufficient. And that is sufficient for our understanding of amplifier and all the transistor applications. Okay, so I think if any doubts, I can try to clear here, or then else you can put your roll number.